PCI Express, officially abbreviated as PCIe, is a high-speed serial computer expansion bus standard designed to replace the older PCI, PCI-X, and AGP bus standards. PCIe has numerous improvements over the aforementioned bus standards, including higher maximum system bus throughput, lower I/O pin count and smaller physical footprint, better performance scaling for bus devices, a more detailed error detection and reporting mechanism, a native hot plug functionality. More recent revisions of the PCIe standard support hardware I/O virtualization. The PCI Express electrical interface is also used in a variety of other standards, most notably in ExpressCard, which is a laptop expansion card interface, and in SATA Express, which is a computer storage interface. Format specifications are maintained and developed by the PCI-SIG, a group of more than 900 companies that also maintain the conventional PCI specifications. PCIe 3.0 is the latest standard for expansion cards that is in production and available on mainstream personal computers. Architecture. Conceptually, the PCIe bus is like a high-speed serial replacement of the older PCI-X bus, an interconnect bus using shared address data lines. A key difference between PCIe bus and the older PCI is the bus topology. PCI uses a shared parallel bus architecture, where the PCI host and all devices share a common set of address control lines. In contrast, PCIe is based on point-to-point topology, with separate serial links connecting every device to the root complex. Due to its shared bus topology, access to the older PCI bus is arbitrated, and limited to one master at a time, in a single direction. Furthermore, the older PCI clocking scheme limits the bus clock to the slowest peripheral on the bus. In contrast, a PCIe bus link supports full duplex communication between any two endpoints, with no inherent limitation on concurrent access across multiple endpoints. In terms of bus protocol, PCIe communication is encapsulated in packets. The work of packetizing and depacketizing data and status message traffic is handled by the transaction layer of the PCIe port. Radical differences in electrical signaling and bus protocol require the use of a different mechanical form factor and expansion connectors. PCI slots and PCIe slots are not interchangeable. At the software level, PCIe preserves backward compatibility with PCI. Legacy PCI systems software can detect and configure newer PCIe devices without explicit support for the PCIe standard, though PCIe's new features are inaccessible. The PCIe link between two devices can consist of anywhere from 1 to 32 lanes. In a multi-lane link, the packet data is striped across lanes, and peak data throughput scales with the overall link width. The lane count is automatically negotiated during device initialization, and can be restricted by either endpoint. For example, a single-lane PCIe card can be inserted into a multi-lane slot, and the initialization cycle auto-negotiates the highest mutually supported lane count. The link can dynamically down-configure the link to use fewer lanes, thus providing some measure of failure tolerance in the presence of bad or unreliable lanes. The PCIe standard defines slots and connectors for multiple widths, A1, A4, A8, A16, A32. This allows PCIe bus to serve both cost-sensitive applications where high throughput is not needed, as well as performance-critical applications such as 3D graphics, networking, and enterprise storage. As a point of reference, a PCI-X device and PCIe device using 4 lanes, Gen 1 speed have roughly the same peak transfer rate in a single direction, 1064 MB per second. The PCIe bus has the potential to perform better than the PCI-X bus in cases where multiple devices are transferring data simultaneously, or if communication with the PCIe peripheral is bidirectional. Interconnect. PCIe devices communicate via a logical connection called an interconnect or link. A link is a point-to-point communication channel between two PCIe ports, allowing both to send-receive ordinary PCI requests and interrupts. At the physical level, a link is composed of one or more lanes. Low-speed peripherals use a single-lane link, while a graphics adapter typically uses a much wider 16-lane link. Lane: a lane is composed of two differential signaling pairs, one pair for receiving data, the other for transmitting. Thus, each lane is composed of 4 wires or signal traces. Conceptually, each lane is used as a full duplex byte stream, transporting data packets in 8-bit byte format, between endpoints of a link, in both directions simultaneously. Physical PCIe slots may contain from 1 to 32 lanes, in powers of 2. Lane counts are written with an A prefix, with A16 being the largest size in common use. Serial bus: the bonded serial format was chosen over a traditional parallel bus format due to the latter's inherent limitations, including single duplex operation, excess signal count and an inherently lower bandwidth due to timing skew. Timing skew results from separate electrical signals within a parallel interface traveling down different length conductors, on potentially different printed circuit board layers, at possibly different signal velocities. Despite being transmitted simultaneously as a single word, signals on a parallel interface experience different travel times and arrive at their destinations at different moments. When the interface clock rate is increased to a point where its inverse is shorter than the largest possible time between signal arrivals, the signals no longer arrive with sufficient coincidence to make recovery of the transmitted word possible. Since timing skew over a parallel bus can amount to a few nanoseconds, the resulting bandwidth limitation is in the range of hundreds of megahertz. A serial interface does not exhibit timing skew because there is only one differential signal in each direction within each lane, and there is no external clock signal since clocking information is embedded within the serial signal. As such, typical bandwidth limitations on serial signals are in the multi-gigahertz range. PCIe is just one example of a general trend away from parallel buses to serial interconnects. Other examples include serial ATA, USB, SAS, FireWire and Rapid I/O. Multi-channel serial design increases flexibility by allocating slow devices to fewer lanes than fast devices. Form factors: PCI Express. A PCIe card fits into a slot of its physical size or larger, but may not fit into a smaller PCIe slot. Some slots use open-ended sockets to permit physically longer cards and negotiate the best available electrical connection. The number of lanes actually connected to a slot may also be less than the number supported by the physical slot size. An example is a A16 slot that runs at A4. This slot will accept any A1, A2, A4, A8, or A16 card, but provides only A4 speed. Its specification may read A16. A size at a speed notation is also common. The advantage is that such slot can accommodate a larger range of PCIe cards without requiring motherboard hardware to support the full transfer rate. Pinout: the following table identifies the conductors on each side of the edge connector on a PCI Express card. The solder side of the printed circuit board is the A side, and the component side is the B side. PRSNT1 and PRSNT2 pins must be slightly shorter than the rest, to ensure that a hot-plugged card is fully inserted. The wake pin uses full voltage to wake the computer, but must be pulled high from the standby power to indicate that the card is wake-capable. Power: all sizes of A4 and A8 PCI Express cards are allowed a maximum power consumption of 25 AW. All A1 cards are initially 10 AW. Full-height cards may configure themselves as high power to reach 25 AW, while half-height A1 cards are fixed at 10 AW. All sizes of A16 cards are initially 25 AW. Like A1 cards, half-height cards are limited to this number while full-height cards may increase their power after configuration. They can use up to 75 AW, though the specification demands that the higher power configuration be used for graphics cards only, while cards of other purposes are to remain at 25 AW. Optional connectors add 75 AW or 150 AW power for up to 300 AW total. Some cards are using two 8-pin connectors, but this has not been standardized yet, therefore such cards must not carry the official PCI Express logo. This configuration would allow 375 AW total and will likely be standardized by PCI-SIG with the PCI Express 4.0 standard. The 8-pin PCI Express connector could be mistaken with the EPS12V connector, which is mainly used for powering SMP in multi-core systems. PCI Express Mini Card. PCI Express Mini Card, based on PCI Express, is a replacement for the Mini PCI form factor. It is developed by the PCI-SIG. The host device supports both PCI Express and USB 2.0 connectivity, and each card may use either standard. Most laptop computers built after 2005 are based on PCI Express. Physical dimensions: PCI Express mini cards are 30A, 50.95 ohm. There is a 52-pin edge connector, consisting of 2 staggered rows on a 0.8 ohm pitch. Each row has 8 contacts, a gap equivalent to 4 contacts, then a further 18 contacts. A half-length card is also specified 30A, 26.8 ohm. Cards have a thickness of 1.0 ohm. Electrical interface: PCI Express mini card edge connectors provide multiple connections and buses, PCIe, 1, USB 2.0, SMBUS, wires to diagnostics LEDs for wireless network status on computers chassis, SIM card for GSM and WCDMA applications. Future extension for another PCIe lane, 1.5 and 3.3 volt power, Mini PCI Express and Msata. Despite sharing the Mini PCI Express form factor, an Msata slot is not necessarily electrically compatible with Mini PCI Express. For this reason, only certain notebooks are compatible with Msata drives. Most compatible systems are based on Intel's Sandy Bridge processor architecture, using the Huron River platform. But for a Msata Mini PCIe connector, the only prerequisite is that there is a switch which makes it either an Msata or a Mini PCIe slot and can be implemented on any platform. Notebooks like Lenovo's T-Series, W-Series, and X-Series ThinkPads released in March/April 2011 have support for an Msata SSD card in their WWAN card slot. The ThinkPad Edge E220 SE420S, and the Lenovo IdeaPad Y460/Y560 also support Msata. Some notebooks use a variant of the PCI Express mini card as an SSD. This variant uses the reserved and several non-reserved pins to implement SATA and IDE interface pass-through, keeping only USB, ground lines, and sometimes the core PCIe 1X bus intact. This makes the Mini PCIe flash and solid-state drives sold for netbooks largely incompatible with true PCI Express Mini implementations. Also, the typical Asus Mini PCIe SSD is 71 ohm long, causing the Dell 51 ohm model to often be referred to as half-length. A true 51 ohm Mini PCIe SSD was announced in 2009, with 2 stacked PCB layers, which allows for higher storage capacity. The announced design preserves the PCIe interface, making it compatible with the standard Mini PCIe slot. No working product has yet been developed. Intel has numerous desktop boards with the PCIe, 1 mini card slot which typically do not support Msata SSD. A list of desktop boards that natively support Msata in the PCIe, 1 mini card slot is provided on the Intel support site. PCI Express external cabling. PCI Express external cabling specifications were released by the PCI-SIG in February 2007. Standard cables and connectors have been defined for A1, A4, A8, and A16 link widths, with a transfer rate of 250 MB per second per lane. The PCI-SIG also expects the normal evolve to reach 500 MB per second, as in PCI Express 2.0. The maximum cable length remains undetermined. An example of the uses of cabled PCI Express is a metal enclosure, containing a number of PCI slots and PCI to ePCIe adapter circuitry. This device would not be possible had it not been for the ePCIe spec. Derivative forms: there are several other expansion card types derived from PCIe. These include low-height card, ExpressCard, successor to the PC card form factor, PCI Express Express module, a hot pluggable modular form factor defined for servers and workstations, XQD card, a PCI Express-based flash card standard by the Compact Flash Association, XMC, similar to the CMC-PMC form factor, Advanced TCA, a complement to Compact PCI for larger applications. Supports serial-based backplane topologies, AMC, a complement to the Advanced TCA specification. Supports processor and I/O modules on ATCA boards. Feature Pack, a tiny expansion card format for embedded and small form factor applications. It implements DUA, one PCIe links on a high-density connector along with USB, I2C, and up to 100 points of I/O. Universal I/O, a variant from Super Microcomputer Incorporated designed for use in low-profile rack-mounted chassis. It has the connector bracket reversed so it cannot fit in a normal PCI Express socket, but it is pin-compatible and may be inserted if the bracket is removed. Thunderbolt, a variant from Intel that combines DisplayPort and PCIe protocols in a form factor compatible with Mini DisplayPort. Serial Digital Video Out. Some 9XX series Intel chipsets allow for adding an additional output for the integrated video into a PCIe slot, M2. PCIe brings PCIe 3.0 to mobile devices, over the MPHY physical layer. History and revisions. While in early development, PCIe was initially referred to as HSI, and underwent a name change to 3GIO before finally settling on its PCI-SIG name PCI Express. A technical working group named the Arapaho Work Group drew up the standard. For initial drafts, the AWG consisted only of Intel engineers. Subsequently the AWG expanded to include industry partners. PCI Express is a technology under constant development and improvement. As of 2013 the PCI Express implementation has reached version 4. PCI Express 1.0. In 2003, PCI-SIG introduced PCIe 1.0, with a per-lane data rate of 250 MB per second and a transfer rate of 2.5 GB transfers per second. Transfer rate is expressed in transfers per second instead of bits per second because the number of transfers includes the overhead bits, which do not provide additional throughput. PCIe 1X uses an 8B/10B encoding scheme that results in a 20%/10 overhead on the raw bit rate. It uses a 2.5 GHz clock rate, therefore delivering an effective 250,000 bytes per second maximum data rate. PCI Express 1.1. In 2005, PCI-SIG introduced PCIe 1.1. This updated specification includes clarifications and several improvements, but is fully compatible with PCI Express 1.0a. No changes were made to the data rate. PCI Express 2.0, PCI-SIG announced the availability of the PCI Express Base 2.0 specification on January 15, 2007. The PCIe 2.0 standard doubles the transfer rate compared with PCIe 1.0 to 5 GTS and the per-lane throughput rises from 250 MB per second to 500 MB per second. This means a 32-lane PCIe connector can support throughput up to 16 GB per second aggregate. PCIe 2.0 motherboard slots are fully backward compatible with PCIe V1X cards. PCIe 2.0 cards are also generally backward compatible with PCIe 1X motherboards, using the available bandwidth of PCI Express 1.1. Overall, graphic cards or motherboards designed for V2.0 will work with the other being V1.1 or V1.0a. The PCI-SIG also said that PCIe 2.0 features improvements to the point-to-point data transfer protocol and its software architecture. Intel's first PCIe 2.0 capable chipset was the X38 and boards began to ship from various vendors as of October 21, 2007. AMD started supporting PCIe 2.0 with its 700 Armenian DRAMs chipset series, and NVIDIA started with the MCP72. All of Intel's prior chipsets, including the Intel P35 chipset, supported PCIe 1.1 or 1.0a. Like 1X, PCIe 2.0 uses an 8B/10B encoding scheme, therefore delivering, per lane, an effective 4-bit S-max transfer rate from its 5GTS raw data rate. PCI Express 2.1 PCI Express 2.1 supports a large proportion of the management, support, and troubleshooting systems planned for full implementation in PCI Express 3.0. However, the speed is the same as PCI Express 2.0. Unfortunately, the increase in power from the slot breaks backward compatibility between PCI Express 2.1 cards and some older motherboards with 1.0/1.0a, but most motherboards with PCI Express 1.1 connectors are provided with a BIOS update by their manufacturers through utilities to support backward compatibility of cards with PCIe 2.1. PCI Express 3X PCI Express 3.0 base specification revision 3.0 was made available in November 2010, after multiple delays. In August 2007, PCI-SIG announced that PCI Express 3.0 would carry a bit rate of 8 GB transfers per second, and that it would be backward compatible with existing PCI Express implementations. At that time, it was also announced that the final specification for PCI Express 3.0 would be delayed until 2011. New features for the PCI Express 3.0 specification include a number of optimizations for enhanced signaling and data integrity, including transmitter and receiver equalization, PLL improvements, clock data recovery, and channel enhancements for currently supported topologies. Following a 6-month technical analysis of the feasibility of scaling the PCI Express interconnect bandwidth, PCI-SIG's analysis found that 8 GB transfers per second can be manufactured in mainstream silicon process technology, and can be deployed with existing low-cost materials and infrastructure, while maintaining full compatibility to the PCI Express protocol stack. PCI Express 3.0 upgrades the encoding scheme to 128B/130B from the previous 8B/10B encoding, reducing the overhead to approximately 1.54%/130, as opposed to the 20% overhead of PCI Express 2.0. This is achieved by a technique called scrambling that applies a known binary polynomial to a data stream in a feedback topology. Because the scrambling polynomial is known, the data can be recovered by running it through a feedback topology using the inverse polynomial. PCI Express 3.0's SATA GTS bit rate effectively delivers 985 MB per second per lane, practically doubling the lane bandwidth relative to PCI Express 2.0. On November 18, 2010, the PCI Special Interest Group officially published the finalized PCI Express 3.0 specification to its members to build devices based on this new version of PCI Express. PCI Express 3.1 specification is scheduled to be released in late 2013 or early 2014, consolidating various improvements to the published PCI Express 3.1 specification in 3 areas: power management, performance and functionality. PCI Express 4.0, on November 29, 2011, PCI-SIG announced PCI Express 4.0 featuring 16 GTS, still based on copper technology. Additionally, active and idle power optimizations are to be investigated. Final specifications are expected to be released in 2014 or 2015. Extensions and future directions. Some vendors offer PCIe over fiber products, but these generally find use only in specific cases where transparent PCIe bridging is preferable to using a more mainstream standard that may require additional software to support it. Current implementations focus on distance rather than raw bandwidth and typically do not implement a full A16 link. Thunderbolt was developed by Intel as a general-purpose high-speed interface combining AA 4 PCIe link with DisplayPort and was originally intended to be an all-fiber interface, but due to early difficulties in creating a consumer-friendly fiber interconnect, most early implementations are hybrid copper-fiber systems. A notable exception, the Sony VAIO-ZV-PC-Z2, uses a non-standard USB port with an optical component to connect to an outboard PCIe display adapter. Apple has been the primary driver of Thunderbolt adoption through 2011, though several other vendors have announced new products and systems featuring Thunderbolt. Mobile PCIe specification allows PCI Express architecture to operate over the MIPI Alliance's MPHY physical layer technology. Building on top of already existing widespread adoption of MPHY and its low-power design, mobile PCIe allows PCI Express to be used in tablets and smartphones. A proposed extension called OcuLink, as a competitor to Thunderbolt, was reported in the press in September 2013. It is the cable version of PCI Express, but despite what its name might suggest, it is intended to be copper-based, and up to 4 lanes wide. Its target launch date is mid-2014. Hardware protocol summary: the PCIe link is built around dedicated unidirectional couples of serial, point-to-point connections known as lanes. This is in sharp contrast to the earlier PCI connection, which is a bus-based system where all the devices share the same bidirectional, 32-bit or 64-bit parallel bus. PCI Express is a layered protocol, consisting of a transaction layer, a data link layer, and a physical layer. The data link layer is subdivided to include a media access control sublayer. The physical layer is subdivided into logical and electrical sublayers. The physical logical sublayer contains a physical coding sublayer. The terms are borrowed from the IEEE 802 networking protocol model. Physical layer: the PCIe physical layer specification is divided into 2 sublayers, corresponding to electrical and logical specifications. The logical sublayer is sometimes further divided into a MAC sublayer and a PCS, although this division is not formally part of the PCIe specification. A specification published by Intel, the PHY interface for PCI Express, defines the MAC PCS functional partitioning in the interface between these 2 sublayers. The PIPE specification also identifies the physical media attachment layer, which includes the serializer, deserializer and other analog circuitry. However, since SATA's implementations vary greatly among ASIC vendors, PIPE does not specify an interface between the PCS and PMA. At the electrical level, each lane consists of 2 unidirectional LVDS or PCML pairs at 2.525 Gbps. Transmit and receive are separate differential pairs, for a total of 4 data wires per lane. A connection between any 2 PCIe devices is known as a link, and is built up from a collection of 1 or more lanes. All devices must minimally support single-lane link. Devices may optionally support wider links composed of 2, 4, 8, 12, 16, or 32 lanes. This allows for very good compatibility in 2 ways. A PCIe card physically fits in any slot that is at least as large as it is. A slot of a large physical size can be wired electrically with fewer lanes as long as it provides the ground connections required by the larger physical slot size. In both cases, PCIe negotiates the highest mutually supported number of lanes. Many graphics cards, motherboards and BIOS versions are verified to support A1, A4, A8 and A16 connectivity on the same connection. Even though the 2 would be signal compatible, it is not usually possible to place a physically larger PCIe card into a smaller slot though if the PCIe slots are altered or a riser is used, most motherboards will allow this. Typically, this technique is used for connecting multiple monitors to a single computer. The width of a PCIe connector is 8.8 ohm, while the height is 11.25 ohm, and the length is variable. The fixed section of the connector is 11.65 ohm in length and contains 2 rows of 11, while the length of the other section is variable depending on the number of lanes. The pins are spaced at 1 ohm intervals, and the thickness of the card going into the connector is 1.8 ohm. Data transmission. PCIe sends all control messages, including interrupts, over the same links used for data. The serial protocol can never be blocked, so latency is still comparable to conventional PCI, which has dedicated interrupt lines. Data transmitted on multiple lane links is interleaved, meaning that each successive byte is sent down successive lanes. The PCIe specification refers to this interleaving as data striping. While requiring significant hardware complexity to synchronize the incoming striped data, striping can significantly reduce the latency of the nth byte on a link. Due to padding requirements, striping may not necessarily reduce the latency of small data packets on a link. As with other high data rate serial transmission protocols, the clock is embedded in the signal. At the physical level, PCI Express 2.0 utilizes the 8B/10B encoding scheme to ensure that strings of consecutive ones or consecutive zeros are limited in length. This coding was used to prevent the receiver from losing track of where the bit edges are. In this coding scheme, every 8 payload bits of data are replaced with 10 bits of transmit data, causing a 20% overhead in the electrical bandwidth. To improve the available bandwidth, PCI Express version 3.0 employs 128B/130B encoding instead, similar but with much lower overhead. Many other protocols use a different form of encoding known as scrambling to embed clock information into data streams. The PCIe specification also defines a scrambling algorithm, but it is used to reduce electromagnetic interference by preventing repeating data patterns in the transmitted data stream. Data link layer. The data link layer performs 3 vital services for the PCIe Express link: sequence the transaction layer packets that are generated by the transaction layer, ensure reliable delivery of TLPs between 2 endpoints via an acknowledgement protocol that explicitly requires replay of unacknowledged bad TLPs, initialize and manage flow control credits. On the transmit side, the data link layer generates an incrementing sequence number for each outgoing TLP. It serves as a unique identification tag for each transmitted TLP, and is inserted into the header of the outgoing TLP. A 32-bit cyclic redundancy check code is also appended to the end of each outgoing TLP. On the receive side, the received TLP's LCRC and sequence number are both validated in the link layer. If either the LCRC check fails, or the sequence number is out of range, then the bad TLP, as well as any TLPs received after the bad TLP, are considered invalid and discarded. The receiver sends a negative acknowledgement message with the sequence number of the invalid TLP, requesting retransmission of all TLPs forward of that sequence number. If the received TLP passes the LCRC check and has the correct sequence number, it is treated as valid. The link receiver increments the sequence number, and forwards the valid TLP to the receiver's transaction layer. An ACK message is sent to remote transmitter, indicating the TLP was successfully received. If the transmitter receives a NAK message, or no acknowledgement is received until a timeout period expires, the transmitter must retransmit all TLPs that lack a positive acknowledgement. Barring a persistent malfunction of the device or transmission medium, the link layer presents a reliable connection to the transaction layer, since the transmission protocol ensures delivery of TLPs over an unreliable medium. In addition to sending and receiving TLPs generated by the transaction layer, the data link layer also generates and consumes DLLPs, data link layer packets. ACK and NAK signals are communicated via DLLPs, as a flow control credit information, some power management messages and flow control credit information. In practice, the number of in-flight, unacknowledged TLPs on a link is limited by 2 factors: the size of the transmitter's replay buffer, and the flow control credits issued by the receiver to a transmitter. PCI Express requires all receivers to issue a minimum number of credits, to guarantee a link allows sending pconfig TLPs and message TLPs. Transaction layer. PCI Express implements split transactions, allowing the link to carry other traffic while the target device gathers data for the response. PCI Express uses credit-based flow control. In this scheme, a device advertises an initial amount of credit for each received buffer in its transaction layer. The device at the opposite end of the link, when sending transactions to this device, counts the number of credits each TLP consumes from its account. The sending device may only transmit a TLP when doing so does not make its consumed credit count exceed its credit limit. When the receiving device finishes processing the TLP from its buffer, it signals a return of credits to the sending device, which increases the credit limit by the restored amount. The credit counters are modular counters, and the comparison of consumed credits to credit limit requires modular arithmetic. The advantage of this scheme is that the latency of credit return does not affect performance, provided that the credit limit is not encountered. This assumption is generally met if each device is designed with adequate buffer sizes. PCIe 1X is often quoted to support a data rate of 250 MB per second in each direction, per lane. This figure is a calculation from the physical signaling rate divided by the encoding overhead. This means a 16-lane PCIe card would then be theoretically capable of 16A, 250 MB per second equals 4 GB per second in each direction. While this is correct in terms of data bytes, more meaningful calculations are based on the usable data payload rate, which depends on the profile of the traffic, which is a function of the high-level application and intermediate protocol levels. Like other high data rate serial interconnect systems, PCIe has a protocol and processing overhead due to the additional transfer robustness. Long continuous unidirectional transfers can approach greater than 95% of PCIe's raw data rate. These transfers also benefit the most from increased number of lanes, but in more typical applications, the traffic profile is characterized as short data packets with frequent enforced acknowledgements. This type of traffic reduces the efficiency of the link, due to overhead from packet parsing and forced interrupts. Being a protocol for devices connected to the same printed circuit board, it does not require the same tolerance for transmission errors as a protocol for communication over longer distances, and thus, this loss of efficiency is not particular to PCIe. Applications. PCI Express operates in consumer, server, and industrial applications, as a motherboard-level interconnect, a passive backplane interconnect, and as an expansion card interface for add-in boards. In virtually all modern PCs, from consumer laptops and desktops to enterprise data servers, the PCIe bus serves as the primary motherboard-level interconnect, connecting the host system processor with both integrated peripherals and add-on peripherals. In most of these systems, the PCIe bus coexists with one or more legacy PCI buses, for backward compatibility with the large body of legacy PCI peripherals. As of 2013, PCI Express has replaced AGP as the default interface for graphics cards on new systems. Almost all models of graphics cards released since 2010 by AMD and NVIDIA use PCI Express. NVIDIA uses the high-bandwidth data transfer of PCIe for its scalable link interface technology, which allows multiple graphics cards of the same chipset and model number to run in tandem, allowing increased performance. AMD has also developed a multi-GPU system based on PCIe called Crossfire. AMD and NVIDIA have released motherboard chipsets that support as many as 4 PCIe, 16 slots, allowing tri-GPU and quad-GPU card configurations. External GPUs. Theoretically, external PCIe could give a notebook the graphics power of a desktop, by connecting a notebook with any PCIe desktop video card. Possible with an ExpressCard interface or a Thunderbolt interface. The ExpressCard interface provides bit rates of 5 Gbps, whereas the Thunderbolt interface provides bit rates of up to 10 Gbps. There are now card hubs that can connect to a laptop through an ExpressCard slot, though they are currently rare, obscure, or unavailable on the open market. These hubs can accept full-sized cards. Examples include MSIG US, Village Instruments ViDock, the Asus XG Station, BPL USPE4HV 3.2 adapter, as well as more improvised DIY devices. In 2008, AMD announced the ATI XGP technology, based on a proprietary cabling system that is compatible with PCIe 8-signal transmissions. This connector is available on the Fujitsu Amilo and the Acer Ferrari 1 notebooks. Fujitsu launched their AMILO graphic booster enclosure for XGP soon thereafter. Around 2010 Acer launched a Dynavivid graphics dock for XGP. Thunderbolt has given opportunity to new and faster products to connect with a PCIe card externally. Magma has released the ExpressBox 3T, which can hold up to 3 PCIe cards. MSI also released the Thunderbolt GUS2, a PCIe chassis dedicated for video cards. Other products such as the Sonata Euro unregistered trademark S Echo Express and M-Logica Euro unregistered trademark SM link a Thunderbolt PCIe chassis in a smaller form factor. However, all these products require the use of a Thunderbolt port, making them incompatible with a vast majority of computers. For the professional market, NVIDIA has developed the Quadroplex external PCIe family of GPUs that can be used for advanced graphic applications. These video cards require a PCI Express A8 or A16 slot for the host side card which connects to the Plex via a VHDCI carrying 8 PCIe lanes. Storage devices. PCI Express protocol can be used as data interface to flash memory devices, such as memory cards and solid-state drives. XQD card is a memory card format utilizing PCI Express, developed by the Compact Flash Association, with transfer rates of up to 500 MB per second. Many high-performance, enterprise-class SSDs are designed as PCI Express RAID controller cards with flash memory chips placed directly on the circuit board, utilizing proprietary interfaces and custom drivers to communicate with the operating system. This allows much higher transfer rates and IOPS when compared to serial ATA or SAS drives. For example, in 2011 OCZ and Marvel co-developed a native PCI Express solid-state drive controller for a PCI Express 3.0 A16 slot with maximum capacity of 12 TB and a performance of to 7.2 GB per second sequential transfers and up to 2.52 million IOPS in random transfers. SATA Express is an interface for connecting SSDs, by providing multiple PCI Express lanes as a pure PCI Express connection to the attached storage device. M2 is a specification for internally mounted computer expansion cards and associated connectors, which also uses multiple PCI Express lanes. PCI Express storage devices can implement both AHCI logical interface for backward compatibility, and NVM Express logical interface for much faster I/O operations provided by utilizing internal parallelism offered by such devices. Enterprise-class SSDs can also implement SCSI over PCI Express. Cluster interconnect. Certain data center applications require the use of fiber optic interconnects due to the distance limitations inherent in copper cabling. Typically, a network-oriented standard such as Ethernet or Fibre Channel suffices for these applications, but in some cases the overhead introduced by routable protocols is undesirable and a lower-level interconnect, such as InfiniBand, Rapid I/O, or NumaLink is needed. Local bus standards such as PCIe and Hypertransport can in principle be used for this purpose, but as of 2012 no major vendors offer systems in this vein. Competing protocols. Several communications standards have emerged based on high-bandwidth serial architectures. These include InfiniBand, Rapid I/O, Hypertransport, QPI, StarFabric, and MIPILLI. The differences are based on the trade-offs between flexibility and extensibility versus latency and overhead. An example of such a trade-off is adding complex header information to a transmitted packet to allow for complex routing. The additional overhead reduces the effective bandwidth of the interface and complicates bus discovery and initialization software. Also making the system hot pluggable requires that software track network topology changes. Examples of buses suited for this purpose are InfiniBand and StarFabric. Another example is making the packets shorter to decrease latency. Smaller packets mean packet headers consume a higher percentage of the packet, thus decreasing the effective bandwidth. Examples of bus protocols designed for this purpose are Rapid I/O and Hypertransport. PCI Express falls somewhere in the middle, targeted by design as a system interconnect rather than a device interconnect or routed network protocol. Additionally, its design goal of software transparency constrains the protocol and raises its latency somewhat. Development tools: when developing or troubleshooting the PCI Express bus, examination of hardware signals can be very important to find the problems. Oscilloscopes, logic analyzers and bus analyzers are tools that collect, analyze, decode, store signals so people can view the high-speed waveforms at their leisure. See also. References. Further reading: Butruk, Ravi. Anderson, Don. Shanley, Tom, Winkles, Joseph Joe Unregistered Trademark, ed., PCI Express System Architecture, Mindshare PC System Architecture, Addison Wesley, ISBN A978-0-321-15630-3 1120 pp. Solari, Edward. Congdon, Brad, Complete PCI Express Reference, Design Implications for Hardware and Software Developers, Intel, ISBN A978-0-9717861-9-6 1056 pp. Willen, Adam. Shade, Justin P. Thornburg, Ron, Introduction to PCI Express, A Hardware and Software Developer's Guide, Intel, ISBN A978-0-9702846-9-3 325 pp. External links: PCI SIGA, the industry organization that maintains and develops the various PCI standards, PCI Express Specification, PCI SIGA, PCI Express Base Specification Revision 1.0. PCI SIG. April 29, 2002. A. PCI Express Architecture, Developer Network, Intel, Introduction to PCI Protocol, Electro-Free-ENSA, An Introduction to How PCIe Works at the TLP Level, Zilli Bossa.